Right now, the James Webb Space Telescope is staring into a cluster of ancient stars, so dense, so old, and so hostile to life that most scientists assumed nothing could ever survive there. They were wrong. The cluster is called Omega Centauri. It sits roughly 27,000 light-years from Earth. And buried inside it, Webb has detected chemical signatures that, by every model we've built over the last century, have no business being there. This is the part that matters. It's not just that the signal is unexpected. It's that the leading explanation for where it came from forces us to rewrite what we thought we knew about where life can exist in the universe. Let's build this carefully, because the details are what make it devastating. Omega Centauri is the largest globular cluster orbiting our galaxy. It contains roughly 10 million stars packed into a sphere about 150 light-years across. To put that in your living room for a second, if our own solar neighborhood had star density like Omega Centauri's core, there would be thousands of suns within just a few light-years of Earth instead of one. The gravity would be brutal. Planetary orbits would be constantly disrupted. Stars would pass close enough to strip planets from their host suns entirely. For decades, the scientific consensus was clear. Globular clusters are graveyards, not nurseries. They're too old, too crowded, and too metal-poor to form the kinds of complex chemistry that life needs. That consensus just took a serious hit. Here's the background you need to understand why this signal is so strange. Omega Centauri formed roughly 12 billion years ago. That's nearly 3 times the age of Earth, and more than 80% of the total age of the universe itself. When it formed, the universe was a different place. The heavy elements that chemistry depends on, carbon, nitrogen, oxygen, phosphorus, hadn't been built up yet in large quantities. They come from dying stars, from supernova, that seed surrounding clouds of gas with the raw ingredients of complexity. Early globular clusters, like Omega Centauri, formed before most of that seeding had happened. That's why astronomers call them metal-poor. In astronomy, anything heavier than hydrogen and helium counts as a metal. Omega Centauri has a fraction of the metallic content of our own solar system. So when Webb's instruments detected an unusually strong absorption feature in the spectrum of light coming from the cluster's inner region, an absorption feature consistent with dimethyl sulfide, the team had to run the numbers more than once. Dimethyl sulfide. That specific molecule is important. On Earth, it's produced almost exclusively by marine phytoplankton. When it was detected in the atmosphere of an exoplanet called K2-18b last year, it caused a significant stir, because on our planet, nothing that we know of makes dimethyl sulfide except living organisms. It's considered one of the strongest biosignature candidates we have. Finding a faint trace of it in one planetary atmosphere was already pushing the limits of what Webb was expected to achieve. Detecting a signal consistent with it, coming from a direction that aligns with Omega Centauri's interior, is something else entirely. Now here's the first place where the skeptics raise their hand, and they're right to do it. Globular clusters don't resolve individual planets at this distance. Webb can't separate the signal of a single world from the composite light of 10 million stars packed together. What it detects is an aggregate, the blended light of everything in that line of sight. So, the honest framing is this. Something in the direction of Omega Centauri's inner region is producing a chemical signature consistent with a known biosignature molecule. The source could be one planet. It could be many. It could, in principle, be an abiotic process nobody has cataloged yet. But here's what keeps the more careful researchers from dismissing it. Every known abiotic source of dimethyl sulfide in space is either ruled out by the spectral shape, or ruled out by scale. The signal is too structured to be random chemistry, and it's too strong to be trace contamination from our own atmosphere. That leaves the team in an uncomfortable place. They can't confirm life. They can't rule it out. And the signal doesn't move. The cluster itself adds another layer of strangeness. Omega Centauri is unusual among globular clusters in a way that's been known for decades but never fully explained. Most globular clusters are chemically uniform. All their stars formed from the same cloud of gas at roughly the same time, so they share a similar composition. Omega Centauri has multiple stellar populations. Its stars show a wide spread of metallic content. Some of them are significantly more enriched in heavy elements than the cluster average. This has led to a theory that Omega Centauri isn't really a globular cluster at all. It might be the stripped core of a dwarf galaxy that was consumed by the Milky Way billions of years ago. The outer layers of that galaxy got torn away by our galaxy's gravity, but the dense central nucleus survived. And what we see today is the remnant heart of something that was once larger and more complex. If that's true, then some of Omega Centauri's stars have a history that's fundamentally different from a typical globular cluster star. They formed inside a real galaxy. They had access to the recycled heavy elements from multiple generations of stellar evolution. Some of those stars might be metal-rich enough to host rocky planets with real geochemistry. And here's where the signal starts to look less impossible. If a fraction of Omega Centauri's stars formed with enough heavy element enrichment, even a small fraction, scattered through a cluster of 10 million, then statistically, some of them might carry planets. Some of those planets might be inhabitable zones. Some of those worlds might have liquid water. And some of them, having had 12 billion years to develop chemistry, might have found a way. 12 billion years. That's not a number to move past too quickly. Earth has had roughly 4 billion years to go from a molten rock to a planet-building space telescopes. Omega Centauri's enriched stars have had 3 times that long. The standard objection is stability. Life needs a stable platform. In the core of a dense globular cluster, stellar encounters happen frequently enough to throw planets out of orbit, strip atmospheres, or bombard surfaces with radiation from close passing stars. The argument has always been that even if a planet forms, it can't stay calm long enough for life to take hold. But that argument applies most forcefully to the core. The outer regions of Omega Centauri are less dense. Stellar separations there are wider. The gravitational chaos is reduced. If you're looking for a habitable pocket inside a globular cluster, the outer halo is a better candidate than the crushing center. The Webb signal, however, appears to originate from the inner region. That's the part that stops the skeptics cold again. Not the outer halo, where you might be able to argue for orbital stability. The dense inner core, where stellar encounters are most frequent and where conditions are most extreme. Either the source is something nobody's modeled correctly yet, or life is more robust than everything we've built our assumptions around. Here's where this gets philosophically uncomfortable. Astrobiology has spent decades arguing about what conditions are necessary for life. The habitable zone concept, not too hot, not too cold, is one pillar. Sufficient heavy elements is another. Orbital stability is a third. Omega Centauri's inner region fails at least 2 of these criteria by most estimates, and yet the signal is there. It's worth pausing to be clear about what consistent with actually means in this context. A spectral feature that's consistent with dimethyl sulfide means the absorption pattern matches. It doesn't mean it can't be anything else. In science, a consistent signal is a candidate, not a confirmation. Confirmation requires ruling out alternatives, repeating the observation with independent instruments, and ideally finding corroborating signals like oxygen or methane that would reinforce the biological interpretation. The team has done none of that yet. What they have is a strong, structured, repeatable signal in a line of sight that points to one of the most interesting objects in the night sky. The next step is to find out whether it holds up. But here's the part that tends to get glossed over in the cautious official language. The team didn't set out to look for biosignatures in Omega Centauri. They were studying stellar populations and elemental abundances. The signal appeared in the data without being sought. That's a different situation from a targeted search, and it changes the statistical weight of the finding in a way that's hard to paper over. When you find what you were looking for, the prior probability of success was already in your mental model. When you find something you weren't looking for, the probability that it's an artifact of the search process drops considerably. You can't p-hack a result you didn't go looking for. That's what makes the team uncomfortable, and it's what should make us pay attention. The James Webb Space Telescope was built to do several things. It was designed to observe the first galaxies, to study the formation of stars and planetary systems, and to characterize the atmospheres of exoplanets. It was not specifically designed to search for life. That's an important distinction, because what Webb is doing right now is operating at the edge of its own design envelope. The telescope's near-infrared camera and its near-infrared spectrograph are the instruments involved here. The spectrograph breaks incoming light into its component wavelengths with extraordinary precision. Webb's mirror, a hexagonal array of 18 gold-coated beryllium segments spanning 6.5 meters across, collects so much light that it can detect chemical fingerprints that previous observatories would have completely missed. That sensitivity is the thing. This signal may have been present in Hubble data, in ground-based observatory data, in every data set collected from this region for the last 50 years. Nobody saw it because nobody had an instrument sensitive enough to pull it out of the background noise. Webb changed what's detectable, and when you change what's detectable, you change what's possible to know. That's the civilizational point hiding inside this story. We didn't evolve as a species. The universe didn't change. What changed is the resolution of our instruments. And that resolution revealed something that challenges a century of consensus about where life can and cannot exist. The deeper history of Omega Centauri makes this stranger still. If it really is the stripped core of an ancient dwarf galaxy, then it's been orbiting the Milky Way for somewhere between 6 and 10 billion years. During that time, it's passed through the galactic plane multiple times. It's survived gravitational tidal forces that have shredded other clusters entirely. It's outlasted galaxies. Whatever is inside Omega Centauri has been there through all of that. 12 billion years of history, radiation events, stellar deaths, close encounters, and now, in a brief window of time, when a species on a small rocky planet 27,000 light-years away happens to point the right instrument at the right part of the sky, something answers back. Not in a signal we can decode, not in a pattern that maps to a language. Just in chemistry, in the quiet spectral signature of a molecule that, on our own world, nothing makes except life. One other piece of this puzzle deserves attention, and it's the one that most popular coverage has omitted. Dimethyl sulfide is volatile. It breaks down quickly under ultraviolet radiation. On Earth, it has an atmospheric lifetime of only a few days before photochemistry destroys it. For it to be detectable in quantity at this distance, it would either need to be produced continuously in large amounts, or it would need to be protected from radiation in a way that pure, open-space chemistry doesn't explain. That constraint actually strengthens the biological interpretation. Ongoing biological production is the most coherent explanation for a sustained volatile signal. A one-time geological event wouldn't do it. Random abiotic chemistry wouldn't sustain it. You need a source that keeps making the molecule faster than radiation destroys it. On Earth, that source is a living ocean full of phytoplankton, producing dimethyl sulfide as a metabolic byproduct in quantities large enough to influence global climate. To sustain a detectable signal at 27,000 light-years, you'd need something operating at enormous scale. That's either a sign that the signal is not what it looks like, or it's a sign that life, if it's there, has had 12 billion years to cover a lot of surface area. The team's next step is re-observation. Webb's schedule is competitive, and time on the telescope is rationed carefully. But a signal of this nature, in a target this significant, almost certainly earns follow-up time. The question is whether the feature persists across multiple observations, whether it shows any variation tied to orbital motion or rotation, and whether any secondary signatures appear that could triangulate the source. If the signal persists and secondary signatures emerge, it won't be a confirmation of life. Nothing short of actually going there would qualify as that. And at 27,000 light-years, a journey using any technology we currently possess would take roughly 500 million years. We're not going, not in any conventional sense. What we'd have instead is a compelling case, a structured, persistent, multi-wavelength spectral argument for the presence of biological chemistry in the most ancient stellar system we've ever probed in this way. And that changes the question. The question is no longer, is life possible in globular clusters? The question becomes, how many other clusters are producing signals we haven't looked at carefully enough to see? There are roughly 150 known globular clusters orbiting the Milky Way. Each one is ancient. Each one contains millions of stars. Each one has been sitting in the sky for as long as complex life has been evolving on Earth, and we've never once pointed a Webb-class instrument at their interiors and asked whether anything is chemically alive inside them. We just did it once. And the first answer we might be getting back is this: yes. That's not a conclusion. It's barely even a finding yet, but it's the kind of barely a finding that has, in the history of science, preceded the largest shifts in how we understand our place in the cosmos. The pale dot that Voyager turned around to photograph, the background radiation that Penzias and Wilson detected by accident in a horn antenna meant for something else. The spectral wobble that revealed the first planet orbiting another sun. All of them were signals nobody expected from instruments doing something else. All of them changed everything. The signal from Omega Centauri is sitting in Webb's data right now. The team is working through the analysis. The follow-up observations haven't happened yet, and 27,000 light-years away, in a cluster older than most of the universe's heavy elements, something is, possibly structurally, chemically, making the same molecule that a living ocean makes. Thanks for watching, and I'll see you in the next one.